Hello. We're going to wrap up today with just one additional example. Here consider two biological tissues in series. This could be, for instance, fat and muscle. And you're looking at how a patch or some drug that you develop is transporting from outside to some concentration inside. And so you have these two materials in series. Of course, we have our partition coefficients, which is the unique part of doing mass balance by diffusion calculation. So we have C1 equals phi. This is material 1 here, and then we have material 2 over here. Phi 1 times C0 on this side, and then C2 equals phi 2 times CL on this side. Now what's interesting is that we have length 1 here, length 2 here. It's what do we do in the middle? What do we do where these two materials meet? We have a balance of partition coefficients there instead of a balance of temperatures, or of concentrations. Remember, with the thermal calculations, we always have temperature equality. Well, we have to have that slightly perturbed here by these partition coefficients at the jump at the interface. But similar to what we had before, we have to have the fluxes on both sides be the same. So J1 has to be equal to J2 at that same position. So the flux in one leaves one, enters the other. So this is a very typical type of transport problem where you have to look at this across two boundaries. It's beyond the scope of this course to do this dynamically. What we can do is let's look at the steady state. So if we go back to the steady state equation, of course we're going to have the diffusion of material inside one, the diffusion of material inside two. We go back to our balance equation. We have d del ci del time equals d del squared ci del x squared. This could be on the left hand, on side 1, this would be di 1, and on side 2 it would be di2, and plus any reaction, but we don't have any reaction in this particular example. So at steady state, we end up solving the equation that we've solved before, 0 equals d squared ci over dx squared. And the solution to this is that C1 equals AX plus B. And then similarly, for the material on the right-hand side, material 2, which we call muscle, would be equal to, let's give these subscripts A1 and B1, A2 times X plus B2. The solution of these differential equations is exactly the same. So we know that in both regions, the steady state distribution will be linear. Now it's just a matter of how do we find all of these constants. Well, we have two equations, and we have 4 unknowns, but we also have 4 boundary conditions. And this is what we have to do. The hard part of this problem is not solving the differential equation. The hard part is solving for all the constants. So the first one is that at x equals 0, we have C1 is equal to that partition coefficient 1 times the bulk concentration on the outside. That's great. Number 2, we have at x equals L, C2 is equal to the partition coefficient times the bulk concentration on the outside. This could be a very small number, especially if the patch or something was just applied. Okay, then we have this region in the middle. So region 3 at x equals L1. We're going to have a continuity of the fluxes here. So we're going to have minus d I1 dc 1 in that side, dx at that position L1 is going to be equal to minus d I2 dc on the right hand side, which would be 2 dx. And And then lastly, we have this condition that is the equivalent of temperature continuity, but at x equals L1, we're going to have a slightly different continuity condition. C over phi1 equals C2 over phi2 for that jump at that interface in the middle. Okay, so we can just start to march through and do successive substitution to solve this. I like to start by making my x equal to 0. Okay, so we can use boundary condition 1 to solve for the first step of this. Okay, so at x equals 0, we're only going to be working with the left-hand side of this. So we're going to have at x equals 0, c1 equals b1 plus a1 times x. That equation makes the substitution. We're going to have phi1 at c0 is equal to b1 plus a1 times our position, which is 0. This term goes away, which gives us our first constant solved for. phi1 equals b equals phi1 times C0, that bulk concentration. So we can rewrite now our equation, at least we have one thing solved for, A1 times X plus phi1 times C0. What do we do next? Let's just go all the way to the right-hand side and then just do the boundary condition at X equals L. We have C2 times equals, at this position, phi2 times the concentration in the bulk over there, which is going to be phi2 times Cl equals b2 plus a2 times that overall position x, which gives us a relationship, at least now that's a little bit more constrained, between b2 and a2. So b2 is equal to phi2c times L minus a2 times L. This is helpful. We can make a successive substitution now to go a little bit further. Okay, so we have our C2 equation. Then it's going to be equal to phi2 times Cl plus a2 times x minus L. So we're making some progress. We've solved for one completely, but now here we have a relationship that is a little bit helpful. So we have two conditions at x equals L1. Okay, the first of these two conditions, well, let's just do C1 over phi1 equals C2 over phi2. Okay, so if we make the substitution in for this equation, we can go back. We have C2 here. We can plug this in for C2 right there. Okay, and then we have our equation for C1 right here. So let's just go ahead and do this. What you end up with is that, let's see, Cl minus A2, okay, here we go. We have C0, okay, plus A1, L1, divided by phi1, okay, equals Cl, okay, minus A2. And we're going to use the we're going to put in the L1, and L1 minus L gives us length L2. That's why there's a minus sign right here. Okay, and remember this is divided by phi2. Now we have a relationship between A1 and A2. We're getting somewhere slowly. The next one we're going to apply is minus di1 dci dx dc1 dx equals minus di2 dc2 dx. Okay, so this is going to be di1 times A1 equals DI2 times A2. These same constants that we have up in this equation. Aha, I think this is going to break it. A1 equals DI2 divided by DI1 times A2. Now we have a direct substitution, so we can eliminate one of our integration constants in this equation. So take this equation and substitute it directly into that equation, and you'll find that A2 now equals DI1 phi1 phi2 times C0 minus CL divided by L2 DI1 phi1 plus L1 DI2 phi2. And of course, by this substitution, we get A1 is going to be equal to DI comma 2 phi1 phi2 times C0 minus CL, all divided by L2 DI1 phi1 plus L1 DI2 phi2. Okay, so this is it. I mean, we've solved for all the constants, A1, A2. We can easily solve now for B2 by substituting in our equation for A2, and we've already solved for B1. So if we go all the way back up to our initial equations, we have C1 equals A1x plus B1, and then C2 equals A2x plus B2. But now through this algebra, we have solved for A1, B1, A2, and B2. So the complete solution is done. It's a little cumbersome to write out, and that's not really the point of this exercise. The point of the exercise is reaching this point right here, which means that our problem is completely done. Now you've solved for the steady state concentration distribution that you can use for calculations for a system of two materials, for instance fat and muscle, that are in series with one another by using the internal boundary conditions as well as the boundary conditions at the edge.